Hello, everybody. Yesterday, we stopped at this point. We talked about the interrupts. Actually, we looked at these steps before, but we are. It looks like my camera is not. Let me try this. Okay, now you have my camera. Okay. We looked at these steps before. We are going to look at it one more time. When the interrupt happens, hardware-wise, the hardware is responsible from saving some important registers in some stack, and it sets up the context for the interrupt service procedure. Now and then the interrupt service procedure is started after stack and context everything is set. And after acknowledging the interrupt to the interrupt controller, our interrupt service procedure can start. This interrupt service procedure is written by the operating system. Now operating system has the control. Okay, at this point the operating system has the control. Before that, these things are done by the hardware. After that, the interrupt service procedure starts. It saves all the registers, necessary registers, most of the time, all the registers. Of course, since we have interrupted a user process or a system process, we have to save them to the appropriate the corresponding entry in the process table, of course, and then we run our interrupt service, whatever it is. If it is an hard disk interrupt, we load the data from the hard disk. If it's a keyboard interrupt, we get the character from the keyboard, and etc. Okay, after we are done with the interrupt service, whatever it is, now we have to give the control back to the interrupted process. Okay, but after the interrupts usually we don't go directly back to the interrupted process. We run the scheduler, because the scheduler might decide that the time is up for this process to run. I am going to switch. So this is an opportunity for us to switch from one process to another process. Okay, so the scheduler runs, and scheduler makes a decision for which the process to run. Then accordingly, our MMU context is set up for the new process, and then we load all of our new registers from the process table, including the program status word and the program counter, etc., and we start running the new process. So this is what happens when the interrupts occur. Hardware and software should work in coordination. The hardware part is hardware part, the software part is handled by the operating system, of course. And this is the lowest level this is the lowest level operating system IO procedure. Actually, it just sits on top of the hardware. It doesn't use any other operating system layers. All the other operating system layers depends on this interrupt handling procedure, okay, including the device drivers. So this is what happens with the interrupt handling. Device drivers, of course, they live on top of the interrupt handlers. And as we said before, every device connected to a computer has a controller. Controller is an electronic device, is part of the hardware. And the driver for the controller is usually part of the operating system, and it is usually written by the manufacturer of this device, whether it's a CD-ROM device or the camera or printer, whatever it is. The driver is provided by the manufacturer. So the manufacturer knows the devices very well, and it knows the controller. And the driver is an interface, software interface between this complicated controller and the rest of the operating system. So this is kind of a interface between this controller and the rest of the operating system. The rest of the operating system doesn't know much about the complications of that device. All it knows is the interface itself. If the interface is clean enough, then I can write program on top of any drivers that okay. So those are the device drivers. As I said before, device driver is generally written by the device drivers manufacturer, and usually the most of the crashes of operating systems are caused by the device drivers provided by the third parties. Okay, you added a new device to your computer, and that device came with its own device driver, and if the device driver is buggy, and since it becomes the part of the operating system. Just a minute, sorry. Okay, so usually the device drivers are the cause of the system crashes, as I said before. So that's a problem. The problem is not solved for most of the operating systems, but there is a solution for some of the systems, and we are going to see it in a few minutes. Okay. Device drivers are many because devices are many, but some of the device drivers are very big, very complicated. For example, this USB serial bus device driver. What kind of devices can you connect through the USB serial bus? It is hard drives, your mouse, your coffee heater, funny USB device, but it exists, right? So they all have to be handled by this USB device driver, and it makes it complicated, but it is very useful for the end users. Okay. There are some operating systems such as Minix, which argue that these are the microkernel operating systems. Okay, they argue that the device drivers should not be part of the operating system's kernel. Okay, so they should be outside of the kernel. So when a new device driver is added to the system, it doesn't become part of the kernel. So if there is a problem, if it crashes, I don't know what's happening. I keep getting, sorry. Efendim. Levent Bey, bir dersteyim ben. Bir 2 saat sonra görüşebilir miyiz? Tamam, ben dersten sonra bakıp size döneyim. Teşekkürler. So the Minix says that the device drivers are not part of the operating system. So when they run, they have to make system calls. Okay, they have to communicate with the kernel like regular user programs. So they will make them a little bit inefficient because every system call means that there is a context switch. That's the negative side. The positive side is they cannot cause any kernel crashes. Okay, kernel crashes. So that's the advantage. Okay, and since the device drivers has to be written very carefully, the operating system designers usually restrict the device driver writers into a standard interface. They say that if you are writing a standard device driver, you have to follow these rules. Otherwise, I will not register you as a device driver. Okay, so if the device driver that you are writing is a block the driver, such as disk, CD-ROMs, it has to be this structure. If it's a character driver, it has to be this structure. So the interface has to be clean. Interface has to be standard. This makes the new device drivers more standard, less opportunities for, less chances for having a buggy driver, and etc. Okay. So device device drivers are like you may think it like this. Okay. Each device driver has an interface, but if they choose their own interface, each one would have a different interface, like in this case. But if I force them to have the same interface for SAT 88 disk driver, for USB or SCSI disk driver having the same interface, exact same interface, operating system will not know any difference between them, and they will have to follow the same rules for all kinds of block device drivers, and less opportunities for having buggy device drivers, and our operating system will be simpler. But if the interfaces are different, then operating systems will be complicated, and there will be more chances of having bugs in the device drivers. So that's the uniform interfacing for device drivers. We prefer, of course, this kind of operating systems to make them more modular, okay, less complicated, better chances of having less buggy operating systems. Okay, so that's what we mean by standard interfaces for the device drivers. Good. So we are still looking at this picture. Actually, where is the picture? The picture is this. I have my hardware, I have my interrupt handlers. We talked about it. We are talking about the device drivers. Then we will talk about the device independent operating system software. So this part of the operating system is part of the operating system, of course, but it is device independent. It doesn't know what kind of device it is working on. Okay. If I am opening a file, I am opening a file on a CD-ROM or a hard drive, doesn't matter for this layer. That's why this is pretty much independent of the device. This is completely written in C, C++, no assembly required. For the device drivers and interrupt handlers, you would need assembly code for some of the time, especially for the interrupt handlers. Okay, let's move on, and maybe I should talk a little bit about practical operating systems. How do we achieve this? How do we achieve this standard interface? This is like, okay, if I am a block device like CD-ROMs or hard disks or USB drives, SCSI disk, whatever, the operations that is possible on these kind of devices are fixed, right? What can I do? Maybe there is a function, there is an operation for opening a file, closing a file. You know the types of things that we can do on the file system, right? Creation of directories, maybe formatting. Okay, so if I say that I have a table of function pointers, okay, I have a table of function pointers for SCSI disk driver. When I write a SCSI disk driver, I make this function table available, and my operating system knows that the first address in the table is for opening the files, the second one is closing, the third one is creating directories, and etc. Okay, so this is what we mean by standard interface between the operating system and the device driver. So each device driver provides the standard table of function pointers, okay? And when I am writing this part of the operating system, device independent part of it, all I am saying is that, okay, I am going to open a file, I am going to create a file, I am going to format this disk, etc. Okay, I am just following these function pointers and I am calling them. I'm calling them. Okay, so the interface is very standard, a table of known length, and each position is for some. Each position is for some. Each position is for some known operation, and I am writing this my code against this one. It's like a Java interface or C++ abstract class. Okay, you know the interface of the Java interface of the driver, and you are writing your code against this interface, these virtual functions, and you are just calling them with the real drivers, and the real drivers knows what to do with those functions. That's how the things are written. Okay, so often the driver holds a table with pointers into self for these functions. Okay, of course each operating system is designed in a different way. For Unix, okay, for the device drivers there is a special directory. It's called devices directory. On my stupid emulation of Unix in this small box, I have this dev directory, but it is, I think it is empty. Why it is not working? Is it not working? Let me start it again. Okay, I start it again. Okay, if I go to the dev directory, these are my device drivers. Okay, these are my device drivers. These are special files, and inside these device drivers, okay, since each one is a file, it's a Unix file, right? Since each one is a file, each one points to an inode, and inside that inode I have the file attributes and etc. And after that, usually what we have the block numbers of the files, right? For these special files, these device driver files, what I have is, okay, two numbers. Okay, it 5 points to an inode which contains the major number, okay, and a minor number. Major number is the driver address of the device itself. Minor number is the unit number. For example, I have many hard drives connected to the same computer, and each one has a different minor number, but they are all using the same driver. Okay, so this is how Unix structures these devices. And when the time comes, if you like to use that disk, what do? You mount that device. At this address, and you give a directory name under the mount directory. Okay, you are saying that I am going to mount this hard drive using this device driver on this position. Okay, so the device and the number are included inside the inode of that file. Since I don't have a real Unix operating system here, can I boot up my real operating system on my desktop? I will try. Or if you have it, you go to that directory and make a list. I don't have, unfortunately. All I have are the terminals. TTY are the terminals. I have this many terminals available for me, and some of the devices are standard error, standard input, standard output devices. Okay, they all are connected to the same device driver, but their units are different. Can I get some information about STD error? Symbolic link is okay. Can I get some information about? So this is the actually the device driver itself. What? Okay, this is connected to the TTY. Okay, my standard TTY1. So a character special file. The major number is 4, the minor number is 1. That's my first unit of my terminal. How about TTY2? TTY2, I don't have TTY2. Oh, TTY0, and there is a TTY0. TTY0, so it is 4 and 0. I wonder where that terminal is. Let me do this. ls, and I am going to send the results to this device, TTY1. As you see, I am getting it on my screen. How about 0? So TTY0 somewhere that I don't have permission. Can I do this? No. TTY0, even if I do this one, I need to be in root mode, I guess. Permission denied. Oh, okay, it is something else. Okay, so I don't want to do these experiments on this stupid system because this is not real Unix. If you do those kind of experiments on your real Unix machines, you will get more meaningful results. And try to see these major and minor numbers and try to see which devices are using the same driver and which devices are using different. Okay, so that's an experiment for you.
Sir, a small question. Why do we have more than 100 terminals?
Well, I don't know. As I said, the answer is I don't know. And the second thing is, let's not try to make sense out of this stupid emulation of Linux. Okay, it is not stupid emulation. I shouldn't say stupid, but I mean, it says that I am handling the kernel, but my file systems are not complete yet. So they are doing something that works, kind of works. Okay, if I do the same thing with my real system, do you guys see my real system? Okay, I guess if I do it that way, or maybe do it perfect. Okay, good. I am sorry for, oh no, you won't see it, right? You won't see it because it is too small. But I mean,
Yeah, we see it, but it's not.
okay, I am going to tell you, and these are my devices. As you see, I don't have that many now. Okay, I don't have that many now. That means that there are many terminals that I can connect to, and on top of it, I have block special devices, and I should have maybe character special devices. Yeah, character special devices here. These are directories, I guess. And some of the devices are already used and mounted. Oh yeah, many of them are mounted actually. So there is a, okay, I think this one is PTS. What is PTS? I don't know what PTS is. Is it my pointer stuff? Mouse stuff? I don't know. I don't know the details of this stuff. You need to look them up. I was trying to find my hard drive. Which one is my hard drive? NTFS. Okay, dev fuse. I couldn't find it. So if you are trying to make sense of something, try to make sense of this stuff, not the stuff on my computer. Okay, back to me. So you do that experiment yourself. Go back and read the chapter about Linux. I think in chapter number 8 or something, and it will tell you about the details of Linux. Okay, both memory, processors, process handling, thread handling, file systems, and I/O. Another issue, if you remember buffering with the I/O software, okay, usually buffering is a very commonly used technique with I/O software. Where is my mouse? Okay, I found the mouse. I need to turn it off. Okay, buffering is a technique that is used a lot. Buffering is a technique that is used a lot in I/O operations. Let's see why we would need buffering. Come on. Okay, it's fine. Let's say if I don't use any buffering at all. So this is the case. I am receiving characters one by one from a modem through internet from somewhere else. And each character is directly written to my user space, and I am reading it character by character or byte by byte. Okay. The problem with this approach is if my program is busy doing something else, if I am late, if I am too slow, okay, this modem doesn't have any place to write its numbers, okay, its bytes. So it will have to wait, and probably I will end up losing data because the data is I am receiving from the internet, but I cannot find any place to write it to. Okay, so reading something byte by byte from some outside world is not a good idea. I need to buffer it. I need to provide some kind of a buffer space like this one. Okay, you say that, okay, this is your 1 kilobyte of space. Write whatever you receive to that space. Whenever there is a data available, the device driver of this modem writes that data to my user space in that buffer. So it is not character by character. Okay, I am trying to fill in this buffer, and the same thing is for the keyboard. I have this keyboard. If a user presses a button, okay, many buttons, doesn't matter if I am reading it or not reading, that data is buffered in some place, right? Okay, so this is a buffered input. So this is good. I will not run into this problem now. But there are some other problems. What is the problem? The problem is this. If my user process is blocked, there is a good chance that this page that belongs to me as a user will be paged out. The operating system may decide to keep that page out of the memory because it needs that memory part. That's going to be a problem. So this device driver, which is a part of the operating system, cannot rely on such buffers. That's why they say that I am going to use this. Okay, keep a buffer in the kernel space. So the device driver is keeping all that data in its kernel space. And kernel space pages, most of the time, are special and they are kept in the memory while this operation is done. When the buffer is full, I transfer all that data to the buffer of the user space. When the user space's pages are available. So I have to keep, unfortunately, two buffers of the same data, in order to not have any problems. But then I am not out of problems now. What is the problem? If this buffer is full, if the user process is blocked again, okay, and this buffer becomes full, where am I going to write the newcomers? Okay, so they invented this technique, double buffering. If this buffer is full and this buffer is full, the user process did not read anything. Now I have a second buffer I am trying to write it to the second buffer while the user process is doing this. Okay, so this is called double buffering. This is called double buffering. Okay, so buffering is used, as I said before, in many places of the operating systems, but especially in the I/O software, buffering is used a lot. Good. Okay. Good. Sometimes they use these circular buffers. So what's a circular buffer? Circular buffer is something like this. Okay. So as a device driver, I write my data to this part, and as the user process, I read my data from this part. Okay. When I write it, this part grows like that, and this one shrinks like that. Okay, this part of the buffer is full. It's a circular buffer. It's like a circular linked list. So instead of using double buffering, maybe it's a good idea to use a circular buffer. Okay, so the hardware advances the first pointer to the device driver as it adds new data. Okay, the operating system advances the second pointer. So one of them is increasing it, one of them is increasing it from the other end. Okay, good. Okay, good. And the buffering doesn't have to be always in this direction, okay? Sometimes we use the buffering in the other direction. For example, when you use the function printf something, okay? You are printing something to the screen. Whenever you call the printf function, that doesn't mean that it is making a system call. Of course, to be able to write something on the screen, you need a system call, but it doesn't happen that way. Printf is smart enough to use a buffer to collect all the printed material, all the characters in a buffer in the user space. When that buffer is full, then it makes the system call. Only after the system call is made, you see your string on the screen. Okay, so if you are printing something character by character, you won't see your characters immediately on the screen. You will see it only buffer is full. Okay, or you will see it when you flush the output buffers. Okay, so if you like to see your printed results immediately on the screen, you flush your print buffers. And I think in C++ you would say cout.flush, yes, something like that. Okay, so when you flush the buffers, okay, all that data in your buffer will be sent to the operating system. So this forces a context switch. This forces a system call. Doesn't matter how many bytes you have in your buffer, 1 byte, 2 bytes, 5 bytes, it's going to make it. Okay, otherwise it will have to wait until 256 bytes are filled in your buffers. So buffering doesn't mean that it always have to be from hardware to software. It can be the other way too. Okay, unfortunately this is most of the time the picture. If I am sending some piece of data over the network, I keep a copy of that data in my user space. When I make a system call, usually the system calls, the first thing that the system calls do is to copy the data to the kernel space, and inside the kernel space, my device driver is going to copy that data to the network controller, the physical device itself. And on the network, while my data is being transferred, many copies of it will be made, and just the opposite procedure will be followed at the other end of the network. So I will end up having 5, 6, 7, 10 copies of the same data over my computers and over my network. This happens. So there's lots of copying, lots of buffering. But the alternative is risk of losing the data. So we kind of accept this kind of a picture. Okay, good. Any questions? Okay, error handling is something that we need to deal with, especially with the I/O. There are many I/O problems that can happen. The user errors, permission errors, I/O errors. Most of the time when I do the I/O, if there is a hard drive problem, mechanical problem, or the surface magnetic surface problems, or the SSD, some part of the SSD becomes unusable, those kind of problems. Um, and there are some serious problems. For example, if you have surface problems on your root block, okay, or inodes track, there will be some serious problems. These errors has to be dealt with, sometimes without telling anything to the user, sometimes informing the user. And these are the ugly parts of the operating systems actually. Somebody has to deal with these, and finding elegant solutions is not that easy. So they all have to be handled one by one. If this happens, but I don't have this, and then this happens, and then this happens, I am going to do this, etc. So they will all need some kind of code to deal with, and operating system designers have to write code to deal with these kind of errors. Okay, finally the main things. Okay, when what happens when you do I/O? Okay, from the user process down to the hardware. Okay, the user process, for example, what are the things that are related to the user processes? You make a I/O call. Okay, for example, I like to open a file in the user process, or I am using open a file, or I am saying that printf something. Okay, so some of the examples: make IO call, open file, write to file, or I like to print something formatted, print format. Okay, or maybe I am doing something spooling. Remember spooling? Spooling is important. For example, the printer spooling. You don't send your files directly to the printer as users. You send them to a spooler process. There is a user process running. Of course, it runs in the user space, but it's part of the operating system. You hand over your data, your file, to the spooler. Okay, the spooler then sends your data to the operating system. Okay, so the spooling happens in the user space. Spooling is part of the I/O, but it happens in the user space. And there is a good reason why we are using spoolers in Unix. It is for the deadlocks, and if we have time, I am going to look at it. Spooling is a good way to prevent deadlocks in operating systems. Okay, so this is the highest level, and we have been using these since we started learning C programming language. Okay, open files, printf, and this is for open, this is for printf, and spooling is sending a file to print. Okay, then we have the part of the operating system now, device independent software. Okay, this is a part of the I/O routines of the operating system. It is good for naming, protection, okay, buffering, allocation of spaces, and the blocking of the processes because of the I/O operations, etc. Definitely in the kernel space, but this part of the operating system doesn't actually know what kind of device it is using. Okay, if I'm doing the naming of if I'm renaming a file, okay, I don't care if it's a hard disk file or SSD file or a network file. Okay, again, for the protection, the protection has to happen independent of the device itself. Okay, this is completely written in C. It doesn't have anything to do with the hardware. Okay, and this is the largest part of the maybe. This is the largest part of the maybe, the along with the device drivers, the I/O software. And then we have the device drivers. Device drivers know a lot about the hardware. Okay, they cannot be device independent because they have to know about the device registers. Okay, they know the meanings of the device registers because they are written by the manufacturers of that device, the device and the device controller. And at the lowest level, I have the interrupt handlers. Okay, what are the tasks of the interrupt handlers? When an interrupt happens, I just handle it. That's it. That's it. And as you see, the device drivers don't ask anything. Don't ask anything about things to do to the interrupt handlers. The device drivers don't talk to the interrupt handlers directly, but interrupt handlers talk to device drivers. Okay, interrupt handler says that an interrupt happened. I am going to copy all that data from the device and into your device driver buffer. Okay, and you wouldn't ask the interrupt handler to do something for you because interrupt handlers are called by the hardware, not by the device drivers. Okay, not by the device drivers. And what are the tasks of the interrupt handlers? You just when the interrupt happens, you just wake up the the driver, and you tell the device driver that the data that you are waiting for is ready now. I copied it already. And at the bottom I have the hardware, and the real hardware makes the I/O operation. So this is the layer structure of the generic I/O software. Generic structure of the I/O software. At the top I have the user processes. At the lowest level I have the interrupt handlers and the device drivers. When you go lower, definitely you need some assembly code, or at least here and there. You need to know the registers, specific register, the address of the registers, so that you can write it. You can write them to those places. Okay, good. Any questions about this picture? Any questions about this picture? Nobody talks to the hardware directly. Nobody talks to the hardware directly other than interrupt handlers and device drivers. Okay? Device drivers directly talk to the hardware. Interrupt handlers, of course, they know about the hardware. But independent software and user processes, they don't talk to the hardware directly.
This can be a repeated question from previous times, but why are the spools in the user space, not in the kernel space?
Well, I mean, you can put anything in the kernel space. It is up to you, but making your kernel larger is not a good idea. Okay, spooling is some kind of a queuing operation. Spooler says that whatever files needs to be printed, I am going to put them in a queue, and whoever has the printer, I will let it use the printer. So this is kind of a queue manager for the printer. Okay, and this queuing operation doesn't need any kernel privileges. All it does is keeps this queue in a fair way. When the time comes for a certain file, it makes a system call and it says that this file needs to be printed. And only that spooler has the permission to say this to the operating system. So in order to not make the kernel much larger than it needs to be, you keep the spooler in your user space. But definitely the spooler is part of the operating system. And we have many things like that, okay? Remember the policy versus the mechanism? The mechanism has to be in the kernel space because it needs to access the special registers, it needs to access the DMA tables and etc. But policy, which has the logic of the algorithms, it doesn't have to be in the kernel space. it makes logical decisions. It is complicated code and possibly includes lots of bugs, but I don't have to run everything in the kernel space. Run that policy algorithms in the user space. Whenever you need the mechanisms to do that, you make a call to the operating system. So keep the operating system smaller, keep the kernel smaller. That's the idea.
Very good.
For example, this formatting IO printf. You don't need to have the root privileges. You don't need to have the privileged access to anything to format a string. Okay, this all can be done in the user space. But to print something on the screen, of course, you need to make a system call. So formatting most of the time is done in the user space, including the buffering of that characters to be printed out. Okay, any other questions? Good. User space IO software like this one, we talked about this, and printer spooling is one of them. Printf formatting is done in the user space. We talked about it. So I guess that's kind of completes the discussion of the IO software. We talked about IO hardware. We talked about IO software. As we have promised before, now we are going to look at the IO devices one by one, starting with the most famous IO device of hard disks. Well, I mean, we are using hard disk less and less, but the ideas are there. Still, the servers and some large computers are relying on the hard disk a lot. This is a picture. That compares two types of disks. This is a disk from 1980s, and this is a disk from 2010s. Okay, so the number of cylinders grew from 40 to 36,000. Tracks per cylinder grew from 2 to 255. Okay, tracks per cylinder. What does that mean? So tracks per cylinder was 2. That means that in IBM 360 kilobyte floppy disk, I had only 2 read-write heads. One for the, where is my floppy disk? Okay, here is my floppy disk. Okay, this is where is the camera? This is my floppy disk. This is inside the floppy, okay, there is a sleeve, and inside the sleeve there is a magnetic disk, and you read your data from this part. Okay, let me make this angle and you can see it. This part also from the other side, this part. So you need 2 heads. Okay. Are there anybody among you who did not use a floppy before? Just raise your hand. Anybody who did not use floppy before? 1, 2, 3. Just 3 people? 4 people?
Sir, I think most of us know this just as a save icon.
But you did not use it. Okay, are there anybody who never touched a floppy disk like this before? A floppy, okay. 1, 2, 3, 4, 5. 5 people did not touch a floppy disk. Okay, so definitely these are dead. I don't know what do I have in this, and I don't think that I have any chances of knowing this ever, because I don't think that in this department I have running floppy disk drives. I don't have it.
Is it 5 quarter or 3.5?
No, this is 5 quarters. 3.5 is here. 3.5 is here, but can I get it? Can I get it? Yeah. What is this? It's a report. Okay, this is a 3.5 desk. And this one is a floppy too. It's rigid, but it's floppy. Why? Because you open it like that. And there is a floppy medium and two heads again. So
I don't think I have ever seen a 5.25 floppy, but I have touched a 3.5 one.
okay, so that's this is an iconic picture of a desk. When you open this Word documents or any place that says save, yeah, do I have it save? No, unfortunately they removed it. Usually they put a small floppy icon next to save
Right
options.
in the quote.
Yeah, here it is. Yeah. So this one is here. This one is a floppy. Okay. This one is a floppy. And okay, let's go back. Let's go back to our slides. So these are definitely dead. Okay. But this was in the 1980s. I had only two tracks per cylinder, and each track, this is a track, right? This is the center, this is a track. Each track had only 9 sectors. So I had, if I do this, so how many tracks sectors I have? 1, 2, 3, 4, 5, 6, 7. I have 8 tracks. I have 8 sectors for this one. And tracks per disk is 720. Anyway, okay. So I am trying to compare this. Oh, this one is important. So seek time is 6 milliseconds between two adjacent cylinders. So that's the smallest seek time that you can have. On the average case, it is 77. And the rotation time, it is 200 milliseconds. That means that every second you are going to rotate your disk 5 times. Okay? And time to transfer one sector is 22 milliseconds. Okay, in 2010s, we have these kind of disks now. Okay, number of cylinders is much larger. Tracks per cylinder is much larger. Instead of 2 heads, now I have 255 heads. Okay, sectors per track again. On the what is this average? Why do they say average? Here it is not average, but this one is average. Can you guess why? What did I say? Okay, I have 8 sectors in this one. Okay, 8 sectors. This one is a sector. This one is another sector. Okay, so when time came to 2010s, we don't talk about tracks per sector or sectors per track. We are talking about average sectors per track. Why do you think so? Okay.
Because there are much more cylinders or tracks.
There are many more tracks, and tracks around the outer edge has more space, right? I can do that. So I can put more sectors in the outer parts, but I cannot put the same number of sectors on the same track inside tracks. It was easy in the previously because I was using the same thing, so I was probably wasting space at the outer tracks, but I don't want to do that. That's why they said it's an average. And the sectors per desk is a lot larger. So, but let's look at this one. Seek time. So how many times is this? Sectors per desk. Can you make a calculation? 720 to 586 million. So let's say this is 1000. Let's say this is 1000. So if this one is 1000, let's get rid of this one. So it is Okay, half a million times more sector. Okay, so number of sectors is half a million times more, but the seek time is only 10 times faster. Okay, and the average seek time is only maybe 20 times faster. So we are talking about half a million times more data, but we are talking about only 10 times faster seek times. The point I am trying to make is the point that I am trying to make is um, this mechanical speeds are not getting much faster, okay, only 10 times or 20 times faster, but the hard drive capacities has increased, okay, by a factor of 800 times, and the transfer times are 16 times better. So this limiting factor here is the seek times, and unfortunately we couldn't get better seek times even for today's, after 20 years, okay, from this hard drive, 10 years from this hard drive, we couldn't get this seek times much better. And so the result is we are limited with the seek times. Whatever we do with the hard drives for our operating systems, we have to be very careful about these seek times and the rotation time and the time to transfer, etc., etc. Okay, so these parts are important, and we are going to look at them in a few minutes after I take 10 minutes of break. Okay, 10 minutes of break. Let's be here around 12:39.
See you in 10.
See ya.
Ya aşağıdan mı geliyor? Yan aşağıdan geliyor. Örnek lavabo götürüyor. Fatih, şey nasıl altında o çocuğun genç çocuk. Yani altına şöyle bir belki İsmail'e şeyi söylemek. Ne yaptın sen ya? Yok orada yani bir de şu çalıştırdığın zaman ses çıkıyor ya. Bu da İsmail'e Bakayışlar. Onun dışında bir problem yok. Yolculuğun çıkmamızda engel bir şey yok. Onu zaten şeyde İsmail'e Şeyi soruyorum. Ha yok, bu değil aslında. Diyelim. Sene geçti. Ama 15 Benim arabada şey vardı ya.
Burada var ama daha pratik.
Gebze daha pratik olabilir.
Yani oraya getirsem mi?
O arabada çalışıyor ama. Arabanın aküyle.
Arabayı buraya getir. Pencereden.
Araba burada zaten. Hemen aşağıda. Bisiklete mi bineceksin?
Evet, dün bindim. Ve mahvettim.
Niye?
Bilmişti şeyi havası.
Havası inince niye mahvediyor?
Gitmiyor, bas gitmiyor.
Benimkinde şişesene.
Dersten sonra şişeyim, şu an nedense yiyeceğim. Hep gidiyor bunun havasını hissediyorum.
Bu kimin?
Bakalım. Lan gittiler hepsi.
Ulan da gitti. Ağacın yok mu? Bunun üstünde ağaç yok mu?
He?
Çay yok mu?
Yok.
Bisiklet teker gibi değil, araba teker gibi değil. Araba tekerinde 30-35 yetiyor, bisiklette 60 basman lazım.
Evet. Ne kadar daralırsa o kadar şey. Şerpin basıncı var ya şerp. Koca şerp var ya, hafif tekerleri bu kadar. İçinde 2 atmosfer mi ne basınç var? Yani dışarıdaki havanın o kadar.
Şart mı ya?
Şerp S-H-R-P. Git. İzle videolarını. Şerp.
Kocaman ne o?
Ben alacağım ondan. 120.000 dolarım olsun. Alacağım.
Ben bir tane şey almayı çok istedim ya. Şu çekiciler var ya. Kaç o çekicilerden alayım. Biliyor musun oradan? Ben de
Alacağız.
sen çekici almadın. Ne o?
Ya sen şerp al ya.
Şarkı nasıl aldın? Sen çekici almadın.
Beraber alalım. Okay, that's the picture. We are going to keep this picture in mind. Whatever we do about hard disk handling, we will keep these numbers, the seek times and the rotational time in mind. and we have to do something about them. So this is maybe the answer to my question before. Why it is 9 sectors per track, now it is 63, okay? If I arrange all of my sectors this way, as you see, the area, the magnetic disk area in the inner track is much smaller than this area. Since each one is the same sector, okay, same sector size, one sector here and one sector there, in order to keep my data reliably at this position, I have to keep this area large. That's kind of waste of space, okay? So they say that why don't we use this two-zone system? So my sectors per track for the inner tracks are, the number of sectors are smaller, but the number of sectors at the outer tracks are larger. So that would be a good solution to get a better utilization of your magnetic disk space. Okay, but the problem with this approach is addressing or writing device independent software for this kind of approach is difficult. Why? Because we assume that I have, let's say, 1,000 tracks, 10,000 tracks. I'm just 1,000 tracks, and for each track I have 100 sectors. So this is much easier to make calculations. It is much faster. So the solution is this: the disks are becoming much smarter. Okay, physically they can implement this, but logically they show themselves like that. So they are providing a virtual geometry to the upper layers of the operating system, but physically they are implementing this. Okay, so since they are smart, okay, their device drivers, their controllers are smart, they can do that kind of virtualization things. Okay, good. Again, about the disks, some people have invented this idea of RAID. RAID is this: redundant array of inexpensive disks. Okay, disks are not getting much faster in terms of seek times, in terms of rotational latency. They are not getting much faster, but they are getting cheaper. So why don't we use many disks at the same time to make reads parallel? Okay, I am going to read the disk in parallel, so I will have much faster virtual disk now. That's called the RAID. Okay, let's look at some RAID structures. Let's look at this structure, for example. This RAID level 2. RAID has different levels: level 0, level 1, level 2, level 3, etc. Level 0 doesn't mean that it is an inferior to level 1 or level 3. Okay, it's just like a label. So RAID level A or level B or something like. So level 0 doesn't mean that it is worse than level 3. But to explain what RAID is, okay, redundant array of inexpensive disks. Okay, let's look at this RAID level 2. RAID level 2 does this. Okay, if you are going to store a byte on your disk, don't put the byte on the same disk, but divide the byte into bits and store each bit on a different disk. So on this system I have 7 or 8 disks, okay, 8 physical disks. For each byte, the first disk stores the bit number 1, then bit number 2, and bit number 3, and bit number 4. Okay, when you are reading or when you are writing your disk, you are using all 7 of them in parallel. Okay, all 7 of them in parallel. That means what? I have a 8-fold, 7-fold speed up, right? I have an 8-fold, 7-fold speed up. Okay, that's good. That's a very good idea, right? That's a very good idea. But the problem with this approach is, again, I need to use many disks at the same time, and I have to synchronize them. their rotations have to be synchronized, because when I start reading from one of them, I should be reading the second bit and the third bit at the same time, so that I don't have time differences between those. So in this case, everything has to be synchronized very, very well. Okay, very, very well. Tell me another problem with this approach. Tell me another problem with this approach, other than the synchronization problem. This RAID level 2. What do you see as the problem with RAID level 2? In terms of reliability, think about the reliability. This is 7 times faster, right? Why is it 7 times faster? Because I have 7 disks. What does that mean in terms of reliability?
I lost one of the disks, then I lost my data.
Yeah, if I lose one of my disks, then I lose all of my data. But the losing one disk is always a possibility, right? If you have a single disk, and if you lose your single disk, then you lose all of your data, right? So what is the difference between using a single disk and 7 disks in parallel?
But if I have 7 disks, then the risk is 7-fold.
Yeah, the risk is 7 times more. So usually what do? There is a 1 in a million chance that my disk is going to fail in a single day. There is a 1 in a million chance. Okay? So if I have 7 disks, each one has a 1 in a million chance. So that means that for a given single day, there is a 7 in a million chance that one of my disks are going to fail. Okay? One of them is going to say. So this is going to increase my chances of having a corrupted disk space. So what are we gonna do? Some people have invented this. So they said, okay, let's use 5 disks. Okay, four of them are for the real storage of the bits. Okay, I am going to distribute my bits into 4 different disks, and I am going to keep a parity disk. So if I lose this bit or this bit or this bit, there is a parity disk available. Okay, there is a parity disk available, and if I lose one of them, I will get my information from this parity disk, because parity is what? Parity is, okay, you add all of them up modulo 1 bit. Okay, it is 0 or 1. I can recover one of them, okay, only one of them, using this parity disk. So you might say that, well, that's not a very good way of keeping your data safe. You can recover only from your one of the derived parities. Then in that case, why don't I use more than one disk? Okay, I can use more than one parity disk. So one parity is for these two and one parity is for these two. Or in fact, maybe I can replicate all of these stuff, okay, to take a backup of each disk, and that way I have more reliable RAID structure. Okay, I have more reliable RAID structure, and since these disks are inexpensive, okay, I put many disks on my RAID system, and reading is parallel. It is much faster, and I can make it more reliable than a single disk too, if I spend more time, if I spend more money. So it can be made both faster and more reliable. Okay, let's look at this RAID level 0. RAID level 0 says that the problem with this approach is, other than the reliability, okay, these disks has to be synchronized. They have to rotate at the same rate. They have to be rotating at the same phase, okay. Whenever I have access to the sector number 0 in the outer track of the first disk, I should be doing the same thing with the second disk. Okay, this is kind of difficult to satisfy. So why don't I keep the first sector on this disk, second sector on this disk, third sector on disk, and fourth sector on disk? So instead of synchronizing the bits, I am synchronizing the sectors. Okay, remember the sectors? On my original disk, these are my sectors. This strip approach says that, okay, sector number 0 will go here, sector number 1 will go here, sector number 2 will go here, and sector number 4 will go here. So I am dividing them sector by sector, so I don't have to synchronize them bit by bit. I don't have to synchronize them bit by bit, but I am synchronizing them sector by sector. Okay, so you might say that, okay, there is a reliability problem like this one. When if you care about the reliability problem, why don't you do this then? Okay, replicate all of your data with 4 more disks. Okay, now you have 2 times more reliable system. If this one crashes, you have your data here. If this one crashes, your data is here. Okay, and reading is going to be much faster. Why? Because I could read my data from all of them. Okay, from all 4 of them. But when you are writing, of course, you have to write both to this part and this part of the disk system. Okay, so level 0, level 1. What is the difference between level 0 and level 1? It is the reliability, right? It is the reliability. Do you think level 1 is more faster to read than level 0? What do you think? Do you think level 1 is faster to read than level 0? I know it is more reliable.
No, there is a compromise, I think. If it's more reliable, there is less speed, so level 1 is, I think, faster than level.
Why? In terms of reading, I am not talking about writing. In terms of reading, why do you think that level 0 is faster?
There is no. I don't remember the English word. İkilik bir durum yok.
What kind of?
Describe it.
What is missing again? So why should it be slower? Because I mean, in level 1, just ignore this part when you are reading it, okay? If you ignore this part when you are reading stuff, level 1 and level 0 becomes the same. This part is for reliability. When you are writing it and writing is in parallel, no problem. Level 1 is not slower than level 0, but it could be faster. Why? Let's say you need to read strip 0, strip 1, strip 2, strip 3, and strip 4, 5, 6, 7 at the same time. Okay? So you could read 4 strips from here and 4 strips from there at the same time. So this is 2 times faster to read. Right? Writing is going to be the same. So this is both reliable and faster. Okay, let's look at them. Okay, level 0 has problems with application that ask data sector by sector. Okay, if the application says that give me sector 0, after I read it, give me sector 1, give me sector 2, give me sector 3, it has speed problems. Why? Because I am accessing the disk one by one. I am not trying to access them at the same time. Okay, so this one has problems in terms of speed if the application is sequential. Okay, by problems I mean that it doesn't take advantage of this RAID structure. It looks like it's a single disk. Okay, that's why they have invented this bit structure. With the bit structure, I don't have this problem. If I am accessing my data sequentially, it is 7 times faster. If I am accessing my data in a batch way, it is 7 times faster. But this one is not. Okay, if I am accessing my data in a batch way, it is fast, but it is sequential, it is not that fast. Okay, because I am accessing the data sector by sector. Of course, we know level 0 has reliability problems. Okay, level 1 is more reliable and reads are faster. Why reads are faster? Because I can read 8 strips at the same time. Okay, I can read 8 strips at the same time. I am reading this, and this at the same time. I cannot do this 8 times faster stuff with level 0. Okay, what else? Let's look at this level 2. Level 2 and level 3 do not use strips. They all require drives to be rotationally synchronized. And level 2 uses okay, parity recovery stuff. If one of the disks crashes, then I can recover from a single crash. Usually, it is not every day that you have a disk crash. Okay, if you have a disk crash, you will have only one of your disks will be crashing. Okay, if one of them crashes, then you immediately replace it with a new disk and you continue. And that's a good way of doing stuff. And then back to the strip approach. Okay, this one is the parity stuff again for the strips disks and the parity disk, and then this one distributes the parities over all the disks. Okay, this one has certain advantages, so I am keeping, this one is not used for reading anything, right? This one is not used for reading anything. This is just for parity, for reliability. So if I distribute this data over five disks, then it is possible for me to read 5 of them at the same time for some cases. So this is faster. Okay, this is faster and this is faster again, but is more reliable because there are more parity bits with this RAID examples. There are many other ways of coming up. There are many other ways of building your RAID systems, and I have only shown you the 6 of them, 6 standard ones. Each one has advantages and disadvantages. So this is some solution for the inefficiencies of the disks, slowness of the disks, and I can use parallel disk structures to make things faster and more reliable. Okay, and if you have many hard drives available for you on your Windows desktop, Windows or Linux provides nice utilities to make RAID structures. You just say that I am going to use these two for hard disk in a RAID structure of level 0, 1, 2, etc. And the Windows will help you in that. Okay, good. Any questions so far? No questions. Okay, let's look at this formatting thing that we talk a lot about, but we did not say much. Okay, so as we know, each disk track is organized into sectors. Each sector, okay, is a hardware addressable part of the track. Sector number 0, sector number 1. So how do you address a sector? You will say that, okay, cylinder number 1, track number 2, sector number 7. Okay, this is how you address a sector. So each one is a sector. So what is the difference between sector and block? Operating system doesn't know much about the sectors. Operating system, and as regular users, we know about the blocks. Usually blocks are groupings of sectors. For example, if I put these three sectors together, I say that this is a single block. Okay, and usually the blocks are 1 sector, 2 sectors, 4 sectors, 8 sectors, etc. It goes like that. So let me make this 2. Okay, so two sectors are making a single block. Okay, but at the lowest level of the hardware disks, we talk about the sectors, and the structure of each sector is like this. When you are reading a sector, at the beginning there is a preamble. This preamble data starts with a certain bit pattern. Okay, that's a special pattern. When your read write head reads this preamble, it knows that it is the starting part of a sector. Okay, there is a special bit pattern, and that special bit pattern cannot happen anywhere on my data. It is arranged that way. Okay, also in this preamble part, you have the cylinder number and sector number and track numbers of this sector. After you read your whole data, there is ECC field. Okay, that's the redundant information that will tell you about the error checksum. Okay, you know how to calculate the error checksums. For example, you add all the data here. Of course, it's going to overflow, but that's okay. I will make that overflowed addition an ECC. I will put it in here. So the data and its addition should match this ECC number. If it is different, then that means what? That means what? That means I couldn't store whatever I stored on this sector. Maybe this sector is a bad sector. Maybe I should mark it as bad. Okay, so disk formatting, low-level disk formatting is this. Low-level disk formatting goes to your disk for each cylinder, track, and sector. It marks each of them with a preamble, with the sector number, cylinder number, track number. Okay, it writes some garbage data and it puts the ECC on there. Okay, you write the preamble, it writes the data, some garbage data, and it calculates the ECC and writes it, and then it reads the same sector. If it is getting the same ECC value, then that means that that sector is a good sector. If I cannot get the same value, then that's a bad sector, and I have to mark it somewhere. This is called low-level formatting. Why do we call this low-level formatting? Low-level formatting doesn't know anything about your file structure or file system. If that disk has a FAT system or inode system or NTFS system, it doesn't know. All it makes it to make it ready for the sectors, to mark all the sectors, to label them, and to see if they are healthy or not. So this is called low-level formatting. Okay, low-level formatting. Remember when you format something, when you format a disk on your Windows, it asks you, should I make a quick format? Do you remember that? Quick format means that I am going to format this disk without doing the low-level formatting. I am going to format this disk by marking the file system related fields only. So I am going to put the inodes back in place, the FAT tables back in place, and that's it. I'm not going to do anything much. But if you are going to do low-level formatting, then it will start from the beginning and it's going to mark all the sectors one by one. It's going to test their health. That's why it's going to take a lot of time. So the quick formatting means that you are putting only file system related information on your desk. Okay, good. Any questions about disk formatting? So at least once in your lifetime of your hard disk, okay, you need to make a low-level format at least once. After that, you don't need it much because usually your sector structure doesn't change unless some of your sectors are going bad. But for that, you have your disk check utilities. Okay, when you do your disk check, okay, it checks the consistency in terms of your file system structure. Also, it checks the health of each sector by writing data and reading data from the same sector to see if they are matching.
Okay. Done fast format, it just overwrites everything to 0. So it goes and puts 0 everywhere instead of just rebuilding the file table again.
Well, if you write 0 everywhere, where is your FAT table? Where is your inode structure? Where is your root directory?
Start with zeroing everything and then you create the file table.
No, well, I mean, writing 0 everywhere on your disk is going to take time. So instead, the quick format means is that your root sector, okay, is going to be formatted, okay, to reflect your changes. So if you are using the inode structure, there is a root file, root inode, okay. I create that root inode, I put it in the place, and I make all the inodes available, all the blocks available, and rest of the disk is left like that, okay. And if you are hacking somebody else's disk, actually, if you are doing quick formatting, low level, not no low level formatting, just quick formatting, all the data are just there on the disk, but it is not structured to be accessed, okay. But if you read it, if you read all the sectors one by one without paying any attention to the file system, you will see that all the old data is there. It is not gone.
Exactly.
Okay.
Even after a low level format, you can still find the data over there.
For certain hard drives, yes, because it is not easy to get rid of all the magnetic signature of the data. If I play my head positions a little bit up and down, you could get the residual data of previous usages. Yeah, it is possible. But for the SSDs, once the things are gone, it is gone. Okay. Good. So this is disk formatting, low level format. Okay. Once the disk is formatting, I mean the low level format, this is the structure. Okay. Where is number 0? Okay. This is my number 0, sector number 0, track number 0, sector number 0. Then 1, 2, 3. It goes like that. And then I have the second track, number 0, 1, 2. And then when it is done, I have the track number. So it looks like I am doing this, and this, and this. Okay. So the 0 is not going that way. 0 is not going 0, 0, 0, 0, but it goes like that and that. Can you guess why? Why are they doing this?
Because of the speed?
Because it is just what?
Because it is spinning. So by the time it moves down, it would have moved already some sectors, right?
Exactly. Suppose my head, read write head is here. My read write head is here. Okay. If I like to move my read write head to the inner track, to this position, okay, it's going to take what? 2 milliseconds? 0.2 milliseconds. 0.2 milliseconds to move my head from this position to this position, but my disk is spinning very fast. 5,200 rotations per minute fast. While I am moving my disk from this position to that position, disk is going to rotate that way. So when I reach the inner track, now I am pointing to this one. So I missed reading 1, 2, 3 sectors. So I do this numbering so that After I move my read-write head from this position to that position, I am positioned on top of this sector. And if I do the same thing again, I am positioned on top of this sector. So this is called skewing. Okay, and the amount of the difference in terms of sector is called skew amount. The amount of cylinder skew depends on the drive geometry. If I have a 10,000 RPM drive, okay, each rotation is 6 milliseconds. If a track contains 300 sectors, that means that every 6 milliseconds I am reading 300 sectors. To read each sector, I need 20 microseconds. Okay, 20 microseconds to read each sector. If the track-to-track seek time is 800 microseconds, then that means that if I move my head from one track to another track, 40 sectors will pass by, and so my cylinder skew should be 40. Okay, in this case my skew is 1, 2, 3. Okay, 3 sectors. But this calculation says that, okay, for this kind of a desk, your skew amount should be 40 sectors. Okay, this is an optimization. If I don't use any skew amounts, what does that mean? It means that I have to, after I move my head from this position to this position, then I have missed the sector number 0. Then I will have to wait the whole 6 milliseconds for the complete rotation of the desk. Okay, complete rotation of the desk, and that's going to take a lot of time for me to complete my I/O. Okay, good. So usually we use this skew amount, and skew amount is calculated depending on your drive geometry, number of rotations per minute, how many sectors you have, the speed of your head, read-write head, etc. It all depends on that.
Is reading inwards biased. If we are reading outwards, or we are seeking for something outwards, it will still going to spin the
it will be penalized very badly. But when you are doing the sequential file writing, you write it in one way, you don't write it the other way. You write your beginning of your file at the outer track, okay, and the continuation of that file comes in the inner track. So usually people read their files from beginning to the end. Okay, this type of access, actually, from track to track access, happens with the sequential accesses. If you are doing random, then you are in trouble already, because every time you need to make lots of track to track seek times and waiting for the rotational latencies and etc. That's why it is expensive to make random reads on a hard drive, mechanical hard drive. Okay, another issue is the interleaving. Okay, suppose this is my sector structure. I read sector number 0. My disk is rotating this way. After I read this one, I read number 1, number 2, number 3. It goes like that. But the thing is this: after I read number 0, I have to make sure that what I read is correct. So I have to make this checksum calculation, ECC calculation. Okay. After I did the ECC calculation, I need to transfer this data to the driver's buffer. Okay. To the controller's buffer, and I do lots of processing. Actually, while I am doing this, the disk is still rotating. When I come back, when I am done with this processing, I see that I cannot read sector number 1 anymore because it is gone. Okay, it is gone because after reading this I did some processing that sector number 1 is gone under my head. What I am seeing is the number 2 now. What should I do? Wait for the whole rotation of the disk, or maybe I get smart and I do this. Okay, while I am reading 0 I read it, I do some processing. While I am doing this processing, sector number 4 passes under my head. When I am done with the processing, now I am seeing number 1. And similarly, number 5 passes and I am seeing number 2. And it goes that way. So this is called interleaving. Okay, interleaving. This is interleaving by 1, single interleaving, and this is double interleaving. 0, if I am doing lots of processing, 1 is here. So at the end, okay, in order to read the whole track, I need 2 rotations of the disk. Okay, I read 0, 1, 2, 3, then 4, 5, 6, 7. But it is better than waiting for the whole rotation of the disk for every sector access. Okay, and this is called interleaving. Interleaving and skewing of the sectors are 2 very common hard disk organization techniques to make things more efficient. Okay, of course these are all specific for hard drives, and you might say that the hard drives are dying anyway. Why are we talking about this? But remember, with the operating systems or any other computer technology, if you solve a problem, that problem is going to come back this year, next year, in 10 years, and in one way or the other way, you are going to see these problems again. Okay? Any questions so far? Any questions? Good. Again, we are still talking about disk optimization techniques. And one final disk optimization technique is the disk arm scheduling algorithms. As we said before, the problem with the disk is the movement of the disk arm, your head movements. It takes lots of time. Okay, the seek time, rotational delay, etc. Okay, so for the rotational delay, I cannot do much because the disk is rotating 10,000 times per minute. Okay, for good drives, so I cannot stop it. I cannot rotate it in the backwards. Okay, it just keeps spinning. Okay, other than interleaving and skewing, I don't do much about the rotation, but I could optimize the head movements. That's what I'm going to do with the disk arm scheduling algorithms. Okay, these algorithms are doing this. Suppose I have a 40 cylinder disk. Okay, and suppose I am at cylinder number 12. Okay, so the operating system, my users are asking to read some data, and it turns out that they need data from cylinder number 2, cylinder number 9, 11, 12, 16, 34, and 36. So what would be your algorithm to make this schedule? Okay, what would be your algorithm to make this schedule? Would you go to the top of the cylinders and read them one by one? Or if I am at 12, okay, maybe I should read 12 first and 11 later, then maybe go back to 16. And so what is your algorithm? Okay, so there are many ways of doing this. Okay, one of them is first come first served. I ordered these in terms of their cylinder numbers, but it does all that data may not be available at the beginning. Maybe I had this, okay? While I am at 11, a new request come for cylinder 1, first one, then 36, then 16, then 34, then 9, and then 12. Okay, since I am receiving this in this order, first come first served algorithm will go to 1, then 36, then 16. So what does that mean? If I am at 1, if I am at 11, to go to 1 I need to travel 10 sectors. To go to 36 I need to travel 36 sectors, 36 cylinders, etc. So 10 plus 35 plus 20, 18, 25, and 3, total of 111 cylinders. If my the cylinder seek time is, let's say, 1 millisecond, so I'm going to spend 111 milliseconds. That's a lot of time. Just for seeking operation, not for reading, just for seeking operation. So it looks like first come, first served is not a very good idea because it keeps going back and forth on my desk. A better solution may be, okay, shortest seek first. Shortest seek first. What do we mean by this? This picture explains it. Okay, if I am at 11, so who is the closest one that I'm going to access? 11, I accessed it. Then I am going to go to 12. Then after that I am going to go to 9. Then after that I am going to go to 16. Then 0, then 34 and 36. Right? So I am looking for the shortest one. So wherever I am, okay, while I am here, maybe I should read the closest one. That's called the shortest seek first algorithm for the disks. Okay, and how could you prove that one of them is better than the other one? Of course, there are no theoretical proofs. We are running simulations. And those simulations are going to tell us which algorithm is better for what kind of processes. Because if I am doing things sequentially, then I think first come first served is as good as shortest seek first, right? Because things are sequential. But if I'm doing things randomly, their performances are going to vary. Okay, shortest seek first. Okay, it took 111 cylinders for the first come first served. For the shortest seek first, it took 61 cylinders. Another algorithm is the elevator algorithm. Elevator algorithm does this. Okay, you know how the elevators work on very large buildings? I have a large building of 100 levels, 100 stories. Okay, elevator is running. So how does it work? Elevator always makes this movement. It goes up and it comes back. While it is doing this, okay, it stops at the locations where there is a passenger to take the elevator, and it takes that passenger. So if my read-write head is like an elevator, then I can implement this one. Because why did they implement the elevators like that? This is more efficient. Otherwise, my elevator, if I am doing the shortest path first, shortest level first, I keep going up and down in the middle of the building, right? I wouldn't go the top level and the lower level. Okay, and these are doing the same thing. So they do this. Start from this one. It is going up. It goes up all the way. While it is doing this, it stops here, stops there, stops there, stops there. And if nobody else wanting me from the upper stairs, now I start coming back. and then I will go up again, up and down, up and down. So this is called the elevator algorithm. And for the elevator algorithm, if I do the same thing again, how many? Okay, total of 60 cylinders. Not surprised because the range of my cylinders is 40. 40 plus 40 is the 80 cylinders at most. Okay. If I do the 80 cylinders, I am going to serve all the requests that I received so far. Some of them are going to wait a little bit, but my overall efficiency is just 60 cylinders. Okay. And most of the time, elevator algorithms are used for disk head access optimization. Good. Any questions? Any questions? It looks like I am way out of my time. Still, more than 100 people are listening to me very patiently.
I have a question about these elevator algorithm, for example. How like what exactly, or which part does it buffer the data that I am reading? If I'm reading in a random axis, so how do I buffer the entire thing?
Well, in your disk driver, okay, you have request. You say that I need data from this track, this track, this track, this track, and you know that's in advance. And
Okay.
each request has its owner. They provide the buffer space. Remember, what do they say? You say that, okay, read this data into this buffer. Okay. All of those requests are owned by somebody from different processes, and I am responsible from reading them from the disk and putting them in the ask buffers. So the buffer problem is already solved. I know where to put them.
I see. I thought they're all by the same request, so I was just
No,
wondering how
well,
do
they are coming possibly from different users and different processes.
Okay, I see that.
Okay, this is a very upper, this is a higher level algorithm. Okay, this algorithm probably implemented in the user space. Okay, this algorithm says that, okay, this is going to be your head movement plan. Now implement this. Now execute this plan, and the execution is done by the kernel. Okay, so that's it for today. I will see you on Monday. So next week is our final week, but I think I owe you 1 or 2 or 3 or 4 classes because I missed some of our classes. And did we lose any classes for any holidays? Did we miss any classes due to holidays? Anyway, I am going to assume that we missed. So I am going to continue. I will finish up with this chapter, and I will talk about a little bit about deadlocks. Then I will talk a little bit about security and the virtualization. And that will conclude our discussion of the operating systems. And at the end of this semester, I will declare you as operating system experts. Well, I mean, experts in quotes. Okay, see you next week.
Have a nice day, sir.
You too.